project. Today I will talk mostly on plastic substrate issues in the flexible display, but I decided to focus on a more imminent issue that I wouldn't talk about OLEDs or OTFT application with plastic substrate. I will focus on more imminent application that I feel that's coming in a couple of years. You may be able to see as a product. So the topic is very limited, but more also focused. So since I'm from a small company, I will give a brief introduction of my company, and then the way I see for the flexible display I will describe, and then issues on the plastic substrate, flexible substrate, and then especially for the LCD application, I will check on some of the developmental issues that we followed through over the years, and then I'll give you a brief summary. First of all, iComponent is now somewhat small size business company now. We started in 2000 as a venture company. Now we are 75 people strong. We have 2 plants making plastic films, including PES, polyisocarbon, polycarbonate, PMMA sheets. Also, we do a lot of different types of coating. So you probably will be able to see some of the product somewhere. Not expecting right now, but on your cell phones or somewhere, you probably use our product. So flexible displays. These are the things you will see this year or next year, or already seen in the market. For example, this one, Seiko Epson's EPD display. It's also flexible, as you see. It's a bent configuration. It's been out as a product. It's about probably $2,000 price watch, and we could see some of those cheaper ones based on LCD product, also on plastic substrate. It's also from Substrate. That's a Korean small company. They are now producing this a lot. So probably this year, close to the end of this year, you will see this kind of sports watch based on plastic substrate. Also, some other product based on a plastic substrate. We all know Samsung Electronics is working on LCDs, full silicon-based LCDs, full color LCDs on a plastic substrate. They proposed a 5-inch sample last year, early last year. Also, end of last year, they gave us a certain hope that they will go for this in a more serious way as they bring out the 7-inch sample. On the bottom, you see famous OLED sample from UDC. And then this is artistic rendition of flexible display. This is, of course, a future display. Everybody is working very diligently and hard to achieve this thing. But we have to go through various steps. I mean, we only now see the monochrome type display for the wristwatches, and then year or two we'll see some of the displays on a flexible substrate, plastic substrate, in cell phones maybe. So we'll have to wait some years to get the kind of display. Okay, plastic substrate. Already, today's speakers already pointed out there are many different types of plastic substrates. I don't want to go detail on this, but as you know, certain metals, metal strips, and even glass. You can laminate the glass with plastic films, or you can coat on the glass with a polymeric material to give certain toughness on the glass. So plastic Why? So you have a choice of plastics, whether it's transparent or semi-transparent. Especially polyimide, so far there has been different type of proposal for colorless polyimide, but so far the polyimide has been dark or yellowish type. So when we think about, choose a plastic substrate, flexible substrate, there are many things that we have to consider. Whether you are on a self-emitting mode like OLED, refractive mode, or transmission mode using backlight. Also, for example, LCDs, they use a polarized light. So you have to consider the kind of thing, whether you could use transparent or non-transparent material, or whether your driving method is active matrix, so it has to be direct processing, or transfer method, or even for the passive matrix, you have to consider what kind of transparent conductive oxide you're going to use. Even the conductive polymer is one choice. So out of a different type of material, you choose one potential substrate. Our choice was a polysulfide material due to its high glass transition temperature. Glass transition temperature for polysulfide is 225, 230 degrees Celsius. And then this is amorphous polymer. So when you process this polymer, we expect to have a very good smooth surface against other type of semi-crystalline polymers. To be used in the LCD, obviously optically isotropic film is required. And as you see in LCDs these days, it's all based on glass. Glass is optically isotropic. So when we develop a plastic film for this kind of application, we need to have an optically isotropic film. This is the reason, when we have a certain LCD, I kind of draw this picture. When we have a linear polarized light going through one medium, and then there is another linear polarized light for detection, this medium generates a certain anisotropy, so that it generates elliptically polarized light, and you will ruin the display. For example, when we use a PET film on the cross-polarized setting, we see a lot of patterns due to the drawing of a PET film during its manufacturing. Then for the PS film we developed, as you see, this is pretty much isotropic. And then interestingly enough, there are two different types of methods to make optical films, optically isotropic film. First of all, solution casting. That's been used for various types of films, including TAC film in the linear polarizer, polycarbonate film for compensator film, basically used in the LCD applications. But process sounds simple. You have a solution and cast it and drive the solvent away, and you have a nice film. But all the time, it has been a Japanese manufacturer delivering those kind of films. And another possible process is extrusion. Extrusion is for us, it's a common process for polymers. PETs and different type of plastic films are driven through the extrusion process. However, when you think about extrusion process, it's very difficult to keep this kind of optical isotropy. So it's very difficult process to have optical isotropy in a low range. At iComponent, we developed an extrusion process. This is a typical extrusion equipment. You have a extruder, and then use a die, and then calendar rolls, and then we do not use any drawing process. For PETs, you extrude it very thick, and then eventually draw to 6 to 8 times. So you have all kind of draw axes in the film, but we didn't use a drawing process. But still, you are able to make the optical isotropy very good. Variation in the retardation is around 10 nanometers. As you see here, this is 1 meter width. When we extrude our film, we make 1.2 meter, about 1.2 meter width. And out of 1.2, we check 1 meter width, and optical retardation is pretty good. So the PS film, we developed this already to be used in the LCD. Then comes to the question of gas barriers. I mean, for the films used in flexible displays, all the time the very lacking property is a gas barrier property. Since the plastic film usually has this kind of moisture barrier or gas oxygen barrier properties. However, for the LCDs, 10 to minus 1, 10 to minus 2 is required. And then for OLED, this morning it was pointed out that even 10 to minus 6 is required to safeguard this display. So it's a very typical topic that we need to discuss, but since I'm focusing on LCD this time, I am at this range, I mean, rather easy to achieve range, so I would not talk too much about it. But basically our system is 200 micron or 125 micron optical film out of PES, and then do various kind of coating. This PES has only probably 60, 70 gram per meter square per day WBTR, I mean, gas barrier property. So we still require certain gas barrier. We apply gas barrier by sputtering. But by putting a sputter layer, usually oxide layers, it certainly improves gas barrier property. However, the problem is the substrate will go through a different type of display manufacturing process, and it's not enough. So we need to put some other material on top, or beneath this sputter layer, gas barrier layer. So then comes the question of adhesion of organic material and inorganic material. ITO is one example, or some other gas barrier materials is another example. So we need to improve the adhesion property, and that certainly is very important because we could make a certain substrate and then send it out to the display manufacturer. They could make certain displays. However, eventually the failure comes in this kind of interfaces. It can be interface between organic and inorganic of our substrate, or it can be interface between our substrate and then other TFTs or some other things that the display manufacturer will put on. So what we try to utilize is atmospheric pressure plasma. In the display industry, atmospheric pressure plasma is starting and getting certain attention for the etching. But for us, etching is not an interest, because we do not want to damage our plastic film coating. Instead, we want to only enhance this reactivity to incoming coating. So we realize this kind of a process gives us freedom to utilize in atmospheric pressure. We don't have to put this film in the vacuum chamber for the certain plasma treatment, and then realize that this treatment is very effective, so cheap. And then we achieved a couple of improvements. First of all, wetting. That's I don't know if you can see here. There are small circles around here. This is a coated surface, and then when we coat the organic coat this substrate, it develops certain pinars. And with atmospheric pressure plasma, we were able to get rid of those pinars, as well as we were able to increase the adhesion property to the complete situation. One other thing we are very much concerned about is thermal shrinkage issues. I mean, we make the film, we make a substrate, then problem is during or before utilization of this substrate, display process, there is always an issue of thermal shrinkage. For example, PET cases, you have a lot of big shrinkage in transport direction. And the direction is rather okay. For PC film we make, we also have for PS films. After we heat treat some time, we realize this shrinkage issues decreases a lot. From this, we did some more study. One of the things is we have to define what's the best condition for the thermal treatment for our substrate. It's all different. I mean, once you coat, we coat on a PS film, the actual stress strain relaxation curve changed quite a bit. I mean, usually PS film alone, it gives a normal amorphous polymer type yield and eventual failure mode. But when we coat with the barriers and other coating, it changes dramatically. And also, during the heat treatment period, we find a certain change in the modulus and then certain variation. It's not big, but still there is. These graphs are shown because we want to show you that even at a 200 degrees C, there is change after a certain time. Also, that can be comparable with a lower temperature, longer time. So we have checked the different type of conditions, and then after 200 degrees C heat treatment, we find at 150 degrees C condition in about 30 minutes, there will be probably very small dimensional change. That means why we do this at 150 degrees C is because we are targeting 150 degrees C process, amorphous silicon or other coating process, or targeted below 150 degrees C. So we feel, 200 degrees centigrade heat treatment for 1 hour, 2 hours will be enough. But one of the problems developed during this thing is yellow index increases at a 200 degrees C temperature. That's a big setback for us. One reason is because there are a couple of reasons why this yellow index increases for the PS. PS itself is not that much affected. However, some of the additives inside the film, as well as the coating that goes on, is not stable enough. I mean, mechanically, dimensionally, it's stable, but optically it changes. So the problem occurs. So now we suggest 170 degrees C for 48 hours is comparable, quite comparable to 200 degrees C heat treatment. So we suggest 170 degrees C for 48 hours for TFT verification at 150 degrees C. So to give you a summary, we developed a PS film with a low optical retardation. That's probably our starting point. How we apply this film for different type of application. For today, I explained basically focusing on the LCD application. So atmospheric plasma treatment is a very key issue for the improvement of the adhesion of coatings. Also, heat treatment, proper heat treatment is required. We could do the heat treatment by ourselves. However, it takes a certain time that our field substrate is utilized at a manufacturing site. Then again, there is a risk that a certain heat cycle may get involved. So another heat treatment may be required. I mean, heat treating plastic film and plastic substrate is a key issue. Right now, we are very much focused on manufacturing the kind of substrate. So spectroscopic method will be used for detecting different type of defects. involved in the coating process or the film or the defect detection is key issue for the substrate. So we are doing some TCO transparent conductive oxide development, including ITO for the passive matrix LCDs. Also, the topic not focused on today, that developing the plastic substrate for OLEDs and all organic display is ongoing within our organization. This work was supported by Frontier Display Project, and I thank you for your attention.